Good morning. Here's a little help on number 19, part A. So we didn't get to these yesterday explicitly in class, but we got to something similar. So here's a chance to look at some variations. The numbers are little, there's some fractions involved, and the intervals aren't as clean. So I thought this would be helpful. So the first thing it asks for is the distance or the displacement that happens on the given interval 0 to 3 under the given velocity function. And the key about displacement is that you just integrate and find that net area. So what happens is there's a negative component and there is a positive component. And when you do the area under a velocity curve, what you're getting is the change in some kind of distance, and it has a directional component. So if it's below the x-axis, you're going to have something that's traveling, let's say, left, and the one on the positive side, all the area on the positive side indicates travel to the right, or east and west, or north and south. So they're just opposing directions of some kind. So now when I integrate this, it's the net accumulation. Like you start at home, you might go 2 blocks south, but then go 5 blocks towards the north. Then your net is going to be 3 blocks of total change with those two combined, is the kind of concept we're dealing with. So here's a look at how you can take it on. Yesterday we said, you can do it with geometry. You can actually get the area of those triangles involved in this linear equation, or you can do the antiderivative and the fundamental theorem where you put the upper bound and lower bound into the antiderivative and subtract. So that's what you're seeing right here. So the first thing is your standard power rule, adding 1 to the degree and dividing by it, and then taking the upper bound in first and the lower bound. And I highly recommend making sure you make separate brackets for that, because it's easy to think you're doing the fundamental theorem in an antiderivative that already has a subtraction sign in it, but actually you want to make sure you put those second brackets in there, upper bound in and the lower bound in to the antiderivative. Subtract the results. So this is what you end up with, and fractionally, it's not the prettiest thing. So things like getting a common denominator, or what you're going to see next. Decided to put them both over 2, subtracting them, and voila, 27 halves is our net displacement. It's not the area of those two triangles. It's actually, thinking of the top triangle, it just means there's more area on the top. Your displacement is more in the positive direction than it was negative, because the negative was only a smaller amount that just took away a little bit. So what we want to compare this to is the next problem, part B, which is total distance traveled, where I just want to know the mileage you're putting on, because if you drive south 2 miles and north 5 miles, that's a total of 7 miles of travel. Now, that would be 3 miles of displacement, but it's 7 miles of total mileage you put on your car. So the question of displacement is how far you are from where you started, which is what we just have now, this 27 halves, versus how many miles you totally put onto your vehicle, or whatever you're traveling with. That would be your total distance traveled. You have to make a small adjustment. You have to do the absolute value of the function, the value of the velocity function, because we want to ignore the negative components of it. We want to think of all the areas, the distances that we move. We want to think of them all as positive. So here comes that piece. So here's our displacement, done with that. Okay, now to do total distance traveled, here comes those absolute value bars. And the way I'm going to tackle it for this one, because the antiderivative process is a little bit different when you see absolute value, it's actually easier to treat this with the area process. So it's a way to, I'll do it this time with just looking at the triangles that I'm making, and I'll add together their areas. So to do the absolute value, you just flip it up. You take the negative parts and put them on top. Okay, so here's a little bit more of a blown up picture of our little scenario. If you look at it, this particular graph, if you set it equal to 0, our velocity function, you'll see that it crosses at 6/7. Okay, so to put it in perspective, and the right end point is 3. So you see that green triangle in there. The right end ends at 3, our interval 0 to 3. And to get the area of each of these triangles, you would do 1/2 base times height. So now that we know the intercept is 6/7, you can see the width of that lower triangle is 6/7. 1/2 times that times its height is 6, because remember the y-intercept of this is -6. So you can see it crossing down below. And then that's the area of, that's like a distance you move, let's say, south of 36/14 units, whatever that happens to represent. And the deal is, when you do total distance traveled, we don't want to think of that as negative like we do when we're doing displacement. Well, that's another positive, mileage that we're putting on. The top triangle, same thing. You're going to do half of its base. Its base is what, 3 minus 6/7. Not a pretty number, but it's just subtracting those two known values. And then the height of it is, of course, we have to find that one. It's a little trickier. So if you know that your endpoint is 3 on the right-hand side, you would just put that 3 into the function, our velocity function, to find out you get 15 as the height. So the height of this one's 15. And then from there, we get the area of that triangle, and it's, let's see, it's got a lot of fractions, 15/7 times 15-ish times a half, and then altogether 225 times a half, or 225/14. Beautiful number. But the idea is we're going to add both of those together. We don't care about one being negative and one being positive here. We want to think of them both as positive for total distance traveled. So this next picture I'll show you is when we'll flip it up top. So in displacement, we actually like to think of what direction they go. The negative below the axis areas we would subtract, and then the top area we would add. But now, what we're doing for total distance traveled, we just think of it as positive. Now I've shown you that in that orange triangle there, 36/14. We're just going to add it to our 225/14 for a total distance of 261/14 units of some kind. Okay, so those are to contrast. What does it mean to have displacement versus what does it mean to have total distance traveled? Hope that helps.